Alright, physics theories, Mr. Thompson here. Let's go through this Michelson experiment and some practice questions. So the equation that we're going to be using, well, there's a few equations. First equation that we'll use is the idea of speed is distance over time. Here, if we're talking about the speed of light, we substitute in c. The other equation that we were introduced to is about his rotating octagonal mirror and a speed of light experiment. So what we have here is the calculation for the speed of light is going to be 2 times d, the distance between the rotating mirror and the fixed mirror, over 1 over n times t, where t is your period, n is the number of sides on the mirror. Let's do some practice questions. So we're looking at the first one here. Michelson experiment, 8-sided mirror, 166,000 RPM, distance between the mirrors 5.8 kilometers. What's the measured speed of light? V is going to be equal to 2 times d. So d is going to be 5.8 E3, and we'll divide that by 1 over 8. Now when we want to calculate t, what we have here is we have really something related to the frequency. So the frequency is 166,000 RPM. If we divide it by 60, then we find the revolutions per second. Okay? So let's do the calculation. 166,000 divided by 60, and I get 2766.6 repeat. Now this will be in hertz. Now we can go ahead and figure out the period from there, which is 1 over the frequency. So it's 1 over 2766.6 repeat. So I'll just invert that answer, and I get 3.61446 e negative 4, and that'll be in seconds. Now we can go ahead and put that in right here. So times 3.61446 e negative 4, and the calculation. Open a bracket on the denominator so I don't get a calc error, and I'll just plug that answer right in there. Alright, so since we have 5.8 limiting it to two significant digits, we got 2.6E8 meters per second. Question number 2. Total time, 83.0 milliseconds for a microwave to travel to a satellite and reflect back to Earth. So this microwave goes up, hits a satellite, and reflects back. So it moves upwards and backward, downwards, back to the Earth. So essentially it goes there and back. So the time here is going to be 83 milliseconds divided by 2. So it's 41.5 milliseconds. Okay? Now that was going to be obviously 41.5 times 10 to the negative 3 seconds. We're looking at how far, or how high it is above the Earth, and so d equals c times t. Here I'm going to use the speed of light as the variable c, the constant c. And so I have 3e8 times 41.5 e negative 3, and the calculation. Alright, I get 1.25, and that would be times 10 to the 367 meters. So if we take off 4 from the exponent here, the power of 10, then we have times 10 to the, take off 3, then I've got times 10 to the 4. And so it's 1.25 E4 kilometers. Question number 3. Okay, during a lightning storm, temperature of the air is 28 degrees centigrade. Speed of sound 347.8 meters per second. If lightning strikes 16 kilometers away, compare the times for the sound and light to reach you. Okay, so for sound, time is distance over speed. And so the distance is 16 kilometers away and 347.8 meters per second. 46 46 seconds. Now for light. Time is distance over the speed of light. And so I have the distance, 16e3 over 3e8. 3e8, and here we go. 5.3 e negative 5 seconds. Okay, I'll stop it there. I did 3 quick examples for you. Okay?